Are we on now? Yeah, ooh, there we go. All right, cool. I hate microphones. All right, let's get ready to discretize. QCD, lattice, all together in one. So, lattice QCD, why? Well, I already said yesterday that when the coupling gets strong, we can't do perturbation theory. We can't just write down Feynman diagrams. I mean, we can. But we would have to write down an infinite number of them and calculate them all and add them all together because they all come in at the same order or even higher, right? If alpha QCD is greater than 1, then more loops means more important, and we don't like loops. So, what do? We turn, well, first off, we need to do something non-perturbative. But there are two parts to what lattice QCD does for us. We have a field theory. A field theory has to be regulated. So we know that field theories are weird. They involve these delta function potentials, which are necessarily singular, right? If you have any interaction between two particles that involve some delta function, maybe you need more of these, I don't know. There we go, we'll make these bars, who knows? I just make stuff up. But the point being that all of our interactions in field theory are local. So you can think of that as being like a delta function potential, a delta function to the singular. This is where the infinities arise in field theory. We usually see them when we write down our first loop integral, and we do it in momentum space, and we see that it scales with some power of the momentum, and so we can't take the momentum to infinity. But really, this is where it comes from, the fact that our interactions are local. So any field theory that we write down that is an interacting field theory is going to need to be regulated, get rid of these infinities. And a momentum cutoff or Pauli-Villar or whatever your favorite regulator works, but it's perturbative. It's saying diagram by diagram, I have these momentum integrals, and I'm going to regulate that integral. So how do we do this non-perturbatively? We go back to this delta function, and we get rid of it. We say we're not going to put the two particles interacting at a single point. We're going to take our space-time and make it be discrete so that we only have to worry about, say, nearest neighbor interactions or things like that. All right, so the lattice provides a regulator rather than having a cutoff on our momenta. We say that our space has some cutoff. We don't allow our space to be continuous. So we can think of going to a equals 0 as like allowing momentum to go to infinity. Okay. But it's even deeper than that. So who remembers back in high school or whenever when you first learned calculus? It was a lot longer ago for me, so you guys should remember it. How did you learn calculus? How did you learn what a derivative was the first time you learned it? What was that? Good, yeah, so for an integral, you would say I have some function. I'm going to break it up into intervals, and I'm going to sum the contributions from each integral. And then you took the limit that the interval goes to 0, but really it was formally defined as a discrete sum, and then you just took the continuous limit. So same thing for a derivative. I think somebody said, when you first learn what a derivative was, it's a finite difference between two spatial points, and then you take a limit that the 2 points approach each other. So all of calculus is actually defined as a lattice. You just forgot, right? You learned how to do the integral, and now you do the integral, and you don't even think about how it was defined in the first place. When you learn about path integrals, and we'll do path integrals a little bit in the next lecture, when you first learn it, you learn that I take some path that a particle follows, and I break it up into little segments, and then I take the limit that those little segments go to 0. So all of calculus, everything that we know, it's actually natural to define this on a discrete space-time, and then just think about the limit as that space-time discretization goes to 0. Okay, so that's how I'm going to start. But just before we get into the math, so when we think about lattice QCD, first and foremost, it's just a way to regulate a field theory. All field theories need regulators. So we're not really doing anything different here. It's just a different kind of regulator. However, it happens to be a regulator that we can define non-perturbatively and that's amenable to numerical techniques. So once you discretize it, you make your path integrals into finite dimensional integrals. You also have to make it a finite volume, but Andrew will talk about that. And then you can put it on a computer. But what I want you to keep in mind is that we're not doing some simulation of some model or something like that. This is QCD, regulated, and we're just solving the integrals numerically because they're really, really hard to do on pencil and paper. Okay. So we have things that look like this in our QCD Lagrangian. I'm going to take this thing and I'm going to dot it into a unit vector just to pick a direction. So I'm taking the derivative in, say, the y direction, whatever. It's just to make this into a scalar function. And so formally, this is the limit of a finite difference. Okay, so we all saw this in calculus. This is actually the formal definition of a derivative. So when we discretize our space-time and do lattice QCD, we're just going to do this. Simple. All right. Now for a little bit, I'm going to talk about kind of a different way of thinking about gauge theories. So we've mentioned gauge theories. We know that the gauge fields are the things that mediate the interaction, blah, blah, blah. If you've had field theory, or maybe last week in your lectures, you were taught that we want some continuous transformation on our fields, and when we do that, then we have to do something funny with the derivative. It has to be a covariant derivative. It's all a little ad hoc, the way that this thing is introduced. But I'm going to introduce it in this formal way that we first learned derivatives in calculus. So if I have a field and we want something that transforms with, I'm just going to do U1 to start with. So this is just a phase transformation. But I want that phase transformation to be dependent on where it is in space-time. All right. So now, looking at this, because we know that our action has these derivatives in it, if we try to perform this transformation on the derivative, it's going to look different for the two different terms, because here, I'm going to get an alpha x, and here, I'm going to get an alpha x plus epsilon n. These two things are at different space-time points, so they're going to see different U1 transformations. So this thing is not well defined under this transformation. We can't say that this object transforms like some phase times that object. So what do? The problem is we don't know how to compare these fields that are at different space-time points. So we define what's called a parallel transporter. And this is going to be some unitary transformation because quantum mechanics, unitary, we like unitary transformations. And I'm just going to define it to be some phase that compares different space-time points. So this is called a parallel transporter because if I act on it, let's see. So what do I want to say? Okay. It's called a parallel transporter because if we act with this onto some field psi of x, it tells us how to think about psi of y through whatever this function is. I haven't told you what it is. It's just some function that compares fields at different points. So this thing has two different space-time points in it. We can require that under this transformation, we get one phase acting to the left and one phase acting to the right. So this one acts on the x coordinate, this one acts on the y coordinate. So now if I apply this thing to a field, here, if you take this and this together, these guys are going to cancel, and this thing transforms as you would expect for a field that's been transported to position y. Has anyone taken GR? I see some yeses, some nos. So this idea of parallel transporter, you learn about also in GR. I took it, but honestly, I don't know that I learned anything. So if you have some curved space-time manifold, and I have a vector here and a vector here, and I want to compare them to each other, let's say I want to dot them to see how much they overlap, I can't just do that on this curved space-time manifold. I have to first transport this guy over to this point so that now I'm comparing apples to apples, I can dot them into each other. So this is the same kind of idea that you learn in GR when you have curved space-time manifolds. Yeah, I guess I can say that at this point. So this parallel transporter in GR, what it does is it transports it to the same location while preserving its length, right? So it doesn't do anything to the vector itself, it just moves it, but according to this manifold. This parallel transporter we can think of as comparing fields at different space-time points while preserving their charges. So this U1 transformation is associated with an electric charge, for example. So we parallel transport it to another space-time point, and we don't change its charge. Charge is conserved. That's the magnitude that's being preserved in this transformation. All right, so now we have this in our pockets. We can go back to our derivative, and now we know how to perform a transformation on something that involves different space-time points. So I'm going to define this new derivative, which is just the same thing, except I'm going to parallel transport one of them to I'm going to parallel transport this guy so that it's at the same space-time point as this guy. I could have done it either way. It doesn't matter because we're taking the limit that epsilon goes to 0. So now under this transformation, this thing is well defined. Technically, I should have written it as alpha to the x plus epsilon n, but I took the limit that epsilon goes to 0, so it just goes to x here. So now this thing transforms as we would like. We can put it into a Lagrangian, which will be invariant under the space-time transformation. Okay, good. So, what is this thing? It's just a function, right? I defined it. So let's look specifically at this infinitesimal parallel transporter. Wow, my handwriting is terrible on the chalkboard, I'm sorry. All right, so epsilon is infinitesimal, so we can take we're taking the limit that epsilon goes to 0, so we can expand this thing for small epsilon. Just do a Taylor expansion. The first term is just u from x to x. That means we've done nothing, so it's just 1. And then the next term is of order epsilon, and it goes like a derivative. At the point x. So this doesn't have to be 1 because I take the derivative first and then I set the two points equal to each other, and then there's more. So this, I just did a Taylor expansion. This thing is just some function that depends only on one space-time point. It depends on x. So I can define this thing to be just some function of x. And I define that function conveniently for my purposes. I pulled out some constant, but it's just a constant. Notice that when I Taylor expanded this thing, I had to give it a direction for the derivative. So this thing is now a Lorentz vector. So this function also has a Lorentz vector on it. So when I expand this thing, I get 1 plus an infinitesimal quantity times some function. I can re-exponentiate this thing. That needs an x. Let's make sure I get everything. And now this looks like some unitary transformation. And it has these fields that depend on x up in the exponent. If instead of an infinitesimal transporter, if I wanted to actually go from point x to point y, which is some space away from it, I can just apply some number of these infinitesimal transformations up until I get to the point that I want to be. So this thing tells me how to move a charged particle from point 1 to point 2, and if I want to build up a lot of them, then I can actually translate it to a finite place away. All right, questions at this point? Epsilon and mu. Yeah, so this is 1 plus something times an infinitesimal quantity. So I can always, and I know that this thing has to be unitary. So I should be able to exponentiate this thing, right? If I expand this thing, I get 1, I get exactly what I had up here. Good. All right. I have another board. Cool. Okay. So now that I have this definition, I can go back to my covariant derivative, this big D that I defined. I have to write it all out again. All right. I did not use my boards judiciously. It's okay. All right, so I have this thing. I can put in my infinitesimal form for u. Okay. Thank you. I have plus. I don't know why. No. We'll come back to the minus sign. It's wrong somewhere in my notes. All right. So gathering terms, I have 1 times psi here. So I can combine this minus this over epsilon. What does that give me? A derivative. And then what I have left over, I guess, is a plus sign. I don't know. I never get minus signs right. Is this. So up to a potential minus sign, this should be what you learned for a covariant derivative when you first learned about gauge theories. Yes. Yep, it should. Thank you. All right, good. So we've re-derived, hopefully, how you first learned this, but in this different kind of language. And there's a reason that I've done this. Another good reason for learning about it this way is that this thing easily generalizes to SUN. So I did this for U1. If instead I had some SUN, for example, if it was SU2, then I would expand these functions in a basis of Pauli matrices up here in the exponent, and that gives me some arbitrary SU2 transformation. So more generally, for SUN, we just expand our fields in a basis of the so-called generators of whatever our SUN is. So for SU3, these are the Gelman matrices. For SU2, they're the Pauli matrices, et cetera. All right. What is next? These are sort of in order. Okay. What's the point? I told you everything is just a lattice anyway. All of calculus, the way we learn it, is just a lattice. And now I have these functions which tell me how to move from one point to the next. So if I discretize my space-time, you can't give a lattice talk without drawing a grid. Now I have some finite distance between space-time points A. I just take everything I've done and I swap epsilon for A, and I don't take the limit that A goes to 0 until I'm actually wanting to get continuum limit results. So I calculate on this thing. If I just set my smallest distance to be A, then I already know how to define my derivatives, my covariant derivatives, all the ingredients that I need for my action. I just write them as finite differences. So what does that mean? These fields, they only depend on one space-time point, which means they live on the intersections of my lattice. Here, they live on the points. What about my parallel transporters? Where do they live on my lattice? The links. They connect, they depend on two space-time points, two adjacent space-time points, because here now epsilon is replaced with A. So the fields connect one space-time point to the next. They live on the links. So in Lattice QCD, we never really talk about these fields A. There's no point. We just talk about the U's. The U's are the thing that live on my lattice. And so everything we're going to write is going to be in terms of U's and size. And when we do our numerical calculation, when we do our path integral, we're going to integrate over all possible U's rather than all possible A's. All right. Not too bad. Okay, good. So we're already halfway there. We've already discretized the covariant derivative. Remember, the QCD action, or the Lagrangian, has a psi bar d/psi in it. So we know how to discretize this thing. We just use this definition. The only thing that's missing now is the pure gauge part of it. And I am just going to be simple and lazy and say, okay, it has to be something that involves my U's, right? Furthermore, it has to be gauge invariant. And remember that under a gauge transformation, this is what my parallel transporter acts like. So it has to involve only links, only the U fields, and it has to be invariant under this thing. Yeah. Yep. Yeah, so the color is hidden in here. So we expand on a basis of the Gelman matrices. So this whole thing is a 3 by 3 matrix. And that will tell us when we go from point 1 to point 2, how we rotate in color space. So it's like we're parallel transporting not only in space, but also in color space, because there can be a rotation as you move from one point to the next, and that's embedded in the indices of our 3x3 matrix. Yeah, the A's, sorry, so these T's are 3x3 matrices. Those 3 indices are the color. They will act on the 3 color indices of the quark field. The A's, so it's like when you expand something, so if I had some arbitrary matrix M and I want to expand it in a basis of Pauli matrices or something, right? So this is like if this is SU2, there are 3 of these. So this index runs over the number of generators of your group. Good. All right, back to gauge action. How do we do the gauge action? So I'm just going to use pure symmetry arguments to give me a gauge action. So if I have some arbitrary parallel transporter and I multiply it by another parallel transporter, Y and Z are probably not great letters to choose, but that's okay. Essentially, all I've done is parallel transport from Y to Z, right? I just broke it up into 2 separate transformations. And if you think about how this thing transforms under a gauge transformation, here you're going to get an e to the I alpha x times e to the minus I alpha x. That cancels. So this whole thing is going to just have a Y phase on the left and a Z phase on the right. So how do I generate something out of my U's that's gauge invariant if I go all the way around and end up back at the same point? So if I do something like this, so here I parallel transform from some number of x's until I end up at the same point. I also have to worry about the fact that there are color indices here, and I want this thing to be color invariant, gauge invariant. So I have to trace over my indices so that I get something that's a scalar in color space. Then if you plug in this transformation, you're going to get all of the ones in the middle are going to cancel each other. You're going to get an e to the I alpha y on the left and an e minus I alpha y on the right, but I'm tracing it, so it's cyclic. I can move this thing over here and it cancels. This whole thing does not transform under a gauge transformation. That's what we want, something that's gauge invariant. So this generic thing, if you think about it on our lattice, what we're doing is oh, I have colors. Look at that. All right. We are moving around our lattice. We're just multiplying a bunch of links together until we end up back at the same point. So this is a closed loop path on our lattice, and it's called a Wilson loop. We all love Wilson, right? I think he had something to do with lattice. And a Nobel Prize or something. So our gauge action has to be composed of these objects. These are the only gauge invariant objects that we have that involve only U fields. I'm lazy, so I'm just going to pick the easiest one. this guy. The smallest possible Wilson loop you can draw is called a plaquette. It's just one square, one loop. So the gauge part of my Lagrangian is going to be something like a trace of what I call USA box. This thing is just one little plaquette. One little complication, these parallel transporters have a particular direction. They go from one point to the next. If I flip the direction, I have to flip my space-time indices on my U, so they're not necessarily the same thing. So this guy goes around one path. In order for this thing to be Hermitian, I have to add to it the dagger, which is going around the other direction. So that's it. That's just the easiest way to write down some gauge invariant thing that involves just my U fields. And I can claim this is where I should have started, right? If we're thinking of calculus as being some limit where our discrete spacetime goes to 0, and I'm to write down some field theory for these fields, this is the thing that I would write down. Now, I could have written it in terms of bigger Wilson loops, and we'll talk about why you may or may not want to do that, but in the end, I am going to take the limit that my A goes to 0, and in that limit, bigger loops should approach the smaller loops. They're just going to give you extra higher order terms that go away when your lattice spacing goes to 0. And if that's confusing now, it's because we're going to talk about it later. All right. All right, so what do I want to leave for exercises? Let's do this part. Just to prove to you that I didn't make this up, well, no, we will leave this for exercise. So you can show that U box plus U dagger box, if I expand somewhere, oh, I guess here, right? We expanded this thing and then plugged in this for that. This thing is the constant. Times F mu nu. Plus higher order. Let's go ahead and call this A now. So if we have time in exercises today, we can do this, but basically you just expand your U fields and this is what you find. And if you think about it, this is actually the only way I do physics. I can't do math anymore. That's why I have notes. I can't do math in front of people. If you think about electromagnetic fields in Maxwell's equations, right? They all involve something like a curl of your B field, how your B field goes around in a circle. And that's exactly what this action is encompassing. It's looking at the curl of some field around a point. As you take that plaquette, the A to 0, that just becomes the curl at a given point. All right, so what about these bigger loops here? When I write down this action, I also made a choice. I said I'm going to call my derivative just a finite difference between two adjacent points. I could have also taken a higher, a point farther away. I could have made it a bigger finite difference because I'm taking A to 0, so that should also approach a derivative. So there are always choices that are made when you define your lattice action. So that is takeaway 1 or 10. I don't know how many takeaways we've had today. But a lattice action is not unique. There are many, infinite many ways to discretize an action. So you're learning about effective field theory, right? So what are the tenets of an effective field theory? It says, choose your degrees of freedom. We've done that. We've chosen our size and our U's. Those are our degrees of freedom. And then write down all possible operators that obey the symmetries of the underlying theory. And come up with some power counting that says how much each order matters so that you don't have to write down an infinite number of orders. So really, when we think about our discretized action, all we care about is that we get QCD in the continuum limit. So it has to be LQCD when A goes to 0, and then everything else just involves some higher dimension operator times, that was supposed to be squared, some power of our lattice spacing so that when we take A to 0, we get QCD. And we've kind of already seen that, right? When we did this, and we take epsilon to 0 or A to 0, we get the derivative, which is the thing we wanted in for QCD. So what do I mean by these higher order operators? Let's do this first. Let's see. Let's go back to just the little d part of it. And we'll think about the choice that we made. So, by choosing adjacent space-time points, I'm going to call this A now. I can Taylor expand this thing for small a, just like I did the U's. And what do I get? So the first term, when A is 0, we just get psi minus psi, which is 0, so that just gives us 0. So the first term is going to be a derivative of psi, which is good. That's the thing we wanted. But there are an infinite number of higher order terms in this Taylor expansion. See, I can't even do a Taylor expansion in front of people. Social anxiety never goes away. So I've Taylor expanded this thing. I get, in the limit that A goes to 0, I get the derivative I wanted. But when A is finite, I have these higher order terms that involve higher derivatives of psi. So I claim, and maybe this is a Yeah, let's do it. We'll do it now. Okay. What if I wanted to do a better job? What if I wanted smaller discretization effects such that I don't have to make A super fine? The finer I make A, the more space-time points in my lattice, and the computational costs go up. And it turns out computational cost is actual money. It costs a lot to run these machines. So we want to reduce our computational time as much as possible. We don't want to have to make A really, really fine. So what can we do? Maybe there's a way to come up with a better derivative that doesn't have this order A error. If we can get rid of it, then maybe the discretization effects come in at A squared, and that would be good. So what do? We don't just take adjacent points. We can also take a derivative that has 2 points. And when we Taylor expand that, it's also going to have something that looks like this. So I'm going to call this guy D2. Oh, geez. All right. By the end of this school, I will be able to write with big chalk. So what did I do? I have my point X, and then I added to it points symmetrically around it. And I just did it symmetrically because I'm smart and I know that that's the way that I need to do it. So if I Taylor expand this thing, the first derivative cancels. That's because I took this symmetric difference on either side. So I'm going to get a derivative in one direction minus the derivative in the other direction. So the first term in this is the second derivative. So this is the lattice proxy for, say, a grad squared, something like that. Plus dot, dot, dot. All right, so if I take as my lattice derivative this one minus A over 2 times this one, then I've canceled this term and I've improved my derivative. So now my errors only come in at A squared. So this is called improvement of your lattice action. You also can improve this very basic plaquette and improve the discretization effects in your gauge action. So this is what I mean by this effective field theory, right? I'm adding operators at a given order in A, and this tells me the order of my discretization effects. If I can improve my action by canceling out the order A terms, then I do a better job and I don't have to beg for as much money. This is called the semantic effective action. And these higher order operators just involve higher orders of our fields. All right. I think that is all I want to talk about today. I do want to mention, though, the other tenet of effective field theories. I write down all possible operators, and what do those operators have to obey? I think I already said it. Can they be totally arbitrary, any function of the fields that I can think of? That's a leading question. The answer is no. What properties do they have to have? Good. They have to be gauge invariant, right? In general, they have to be invariant under any symmetry operation of my underlying theory. So we wrote down yesterday all the different symmetries of QCD, right? So these operators have to obey all of those symmetries. And I spent a lot of time talking about chiral symmetry. So chiral symmetry is going to be an issue. We'll do that next time. But if we're going to think of this as being some effective action that approaches QCD in the continuum limit, then we should expect our operators to obey chiral symmetry, or at least to obey it and break it in the same way that QCD does. So we'll see next time what happens. Cliffhanger.
Thank you. All right, do we have any questions or comments for discussion for Amy?
Hi, and I'd like to thank for the lectures. I have curiosity about the trace of U square. I don't understand very well, but I remember that you are mentioning about the square, the unity square of the lattice. Could you explain the LG proportional to trace of sum of U's again?
Here?
Yes.
Yeah, so I can write it down explicitly. So this U sub plaquette is just this object involving 4 links. So it's going to be trace of, say, let's go x to x1, and then we go from x1, say, to y1, so in the y direction. Let's see if this actually makes a closed loop. So we would go over, and then up, and then back over to x. No, that's too soon. Wait, we're at y1. So, no, we're still at x1, x1, y1. Ah, this is a dagger. No. Yes. From over, and then, oh, it's because I started here. All right. Let's go x2 to x1. Once again, why I need notes. So basically, just going around, this should also be a dagger. Going around my loop. And then the trace is over space-time, so we're going to be summing over all space-time points and also tracing over the color indices, because remember, these things are matrices. D, E, and then we're going to trace A and E. And then the dagger of that is going to go around in the other direction, so you're just going to dagger them all. I'm not sure where you said something about squaring. Oh, this square. Got it. I thought you meant like this. Got it.
Are there any other questions?
Oh, I should also say, when we do the action, we're going to have to sum everything, right? Because the action is integrating over space-time. That integral just becomes a sum over all lattice sites, all plaquettes.
Questions, comments, gripes, complaints?
Now you can go out and calculate something. Code it up.
I have curiosity about other formulations about the lattices. I ever read about this formulation, but has another famous, or I don't know.
You mean other like improvements of the action, or?
No, another formulations. I don't know. Every formulation for the lattice is the same way,
Oh, I don't know anything about the Hamiltonian formulation.
Yeah, there are, do you have a comment on this? Okay, Sebastian has done some work on some other
Yeah.
formulations.
I only know how to do path integrals. I can't do quantum mechanics.
I actually had a similar question with different formulations in a different sense. What happens if we don't use a square lattice, but hexagonal lattices or triangular lattices, etc.? And a comment about Hamiltonian formalism is it's beautiful. And it's very popular now because of all the quantum simulation that people are excited about. And they say quantum simulations can be used to study real-time dynamics. And Hamiltonian formulation seems natural to study that because you can write evolution operator as an exponential of a Hamiltonian. I think that Hamiltonian formulation of lattice QCD came out almost immediately after the path integral formulation appeared by Kogut and Saskind. And the interesting thing was that it was initially understood as a way to solve QCD non-perturbatively with pen and paper, because you can perform strong coupling expansion or perturbation theory in strong coupling using Hamiltonian formulation and just compute the spectrum of hadrons. And the problem is, and it's unsolved until today, that the strong coupling expansion is detached from the continuum limit. So you cannot say that your spacing discretization is small, and thus you cannot really say whether the theory that you expanded has anything to do with reality. So that's a fun fact. But it's a very interesting and rich topic.
Yeah, I mean, you can do the same strong coupling expansion in the path integral formulation as
Yes.
well. You just do a group integration over your
character expansion, which is another beautiful piece of math.
Yeah. So that's not unique to Hamiltonian, that's just strong coupling. But yeah, so as you just said, remember last time when we talked about the coupling of QCD, and let's do it in position space. So as R goes to 0 or momentum goes to infinity, we have asymptotic freedom. So our coupling goes to 0. So it's actually the weak coupling limit as A goes to 0 that gives us lattice QCD. So it's a little counterintuitive because you think about, well, we're trying to do this for strong coupling. But the coupling is just a field theory device. It's not actually connected to an observable until you actually calculate that observable. So the lattice action, it's the weak coupling limit, the coupling of your lattice action that gives you the thing that you want. And so the strong coupling regime would be when A is finite or large, really. Yeah, your comment about different lattice configurations, people have done this. It's ugly. It's numerically, I think, difficult, and also it's tricky to think about the gauge invariance on these.
Advantages like symmetry?
Yeah, so I mentioned yesterday my first PhD project, trying to put chiral gauge theories on the lattice. So we're going to talk next time about how these actions screw up chiral symmetry for us. But one idea is to use different geometry for our lattice. So we were looking at things like cylindrical domain walls and trying to see if in these curved coordinates, if we could maintain this chiral gauge theory. So it's something people try to think about because there's a no-go theorem about chiral symmetry in the lattice for the square lattice. So, you know, people get around this by, say, going to higher dimension where things are allowed. You could also think about formulating them differently, but there are also efforts to put GR on a lattice where they like triangulate the space, the curved manifold, and I don't know how far that got, but yeah.
One question: how to fix a gauge in the lattice?
How do you fix a gauge? So you don't have to, right? This thing is gauge invariant, and so it doesn't matter if there are redundant degrees of freedom in this A because we're using the object U rather than A. You can gauge fix, so you can say, set all your links in one direction to be constant. I don't remember which gauge that is, but people do this especially for like QED on the lattice where you do have to gauge fix. But yeah, you don't have to. But what you would do is just set some subset of your links to be, say, 1, and don't allow the dynamical fields in that
For
direction.
example, if it is a Coulomb gauge or Lorentz gauge, so the links should be like, it's different. Which links should we fix or which? So
Yeah.
that's the matter, right? Okay.
Mm-hmm. Yep, exactly.
We have a comment which I was going to make, but Sebastian.
Yes. I'm not sure if I have the same comment as a lover of gauge fixing on lattice. Yeah, if you want to fix the Coulomb or Lorentz gauge, it's an extremely tricky subject because in the non-abelian field theories, you have the problem of so-called Gribov copies. So this is a problem that's solved perturbatively by saying you work in a weak coupling limit, and so gauge fixing is a procedure that's uniquely defined. If you work in non-perturbative regime, then it cannot be shown, I think, in general, and probably even in simple cases, it cannot be shown that by performing some kind of gauge fixing procedure on the lattice, you are free of this Gribov copy problem. That is, that, for example, when you do path integral integration, so you sample over different configurations, that you're not overcounting certain gauge fix configurations that are just Gribov copies of one another. So that's, I'm not sure if it's a solved problem. I think it's not a solved problem in general. You need to study this case by case using some techniques. In general, gauge fixing is formulated on the lattice of this nonlinear gauges, or rather curved space gauges, like Coulomb or Lorentz by some functional minimization. And then you just need to study how this functional behaves.
Yeah, so for example, if you put QED on a lattice, there's an IR problem, and you can solve it by some gauge fixing procedure, but in general, it either destroys your transfer matrix, which is e to the Hamiltonian, or it destroys locality or other things that we hold dear when we talk about field theory. Yep, but for just QCD, you don't have to.
Let me echo what Amy said for QCD. If you're interested in physical observables, say a hadron mass, then you don't need to gauge fix like you do in, so if you learn gauge theories perturbatively, there's the Fadeev-Popov procedure, which you do this complicated technique in order to make sense of these diverging path integrals. And then at the end of the day, it's gauge invariant. Where lattice, things are finite. So, any sort of redundancies get canceled out in the usual correlation function you're computing anyway. So, as Amy said, if you're interested in physical observables or things are gauge invariant, then there's no need to regulate. But if you're interested in gauge variant quantities, as Sebastian said, then you need to worry about these highly technical issues.
Right, but a gauge variant observable would not be a physical observable.
Correct.
Yeah.
Yeah. All right. Any further questions or comments? If not, we will meet back here at 2 p.m. for the afternoon session. Thank you.